Equilibrium constant expressions are equations that describe combinations of reactant and product concentrations that will be at an equilibrium state. We can write an equilibrium constant equation. We start with a capital K. It needs to be capital, not lowercase. Will be the concentration of the products raised to their stoichiometric coefficients divided by the concentration of reactants raised to their stoichiometric coefficients. In this example of the synthesis of ammonia from nitrogen gas and hydrogen gas, the only product here is ammonia. I'm going to put it in square brackets. The square brackets denote concentration. Now, ammonia has a coefficient of 2. There's 2 ammonia molecules produced. And we're going to multiply all the concentrations of products together. So essentially 1 ammonia times another ammonia would be ammonia squared. That coefficient of 2 becomes an exponent in the equilibrium constant expression. Okay, that's all the products divided by the reactants. And there's 2 reactants in this case, nitrogen gas and hydrogen gas. And we need to raise these to their stoichiometric coefficients as well. The stoichiometric coefficient for nitrogen there is 1, so we raise it to the exponent of 1 and we can leave that out. But hydrogen would be raised to the 3rd power. And so this would be the equilibrium constant expression for this particular reaction. Anytime that this equation gave the same constant value would be in an equilibrium state. Now we can calculate this value at any point, and we would call that a reaction quotient. It's Q. That may not be important in your course, but when the system is at equilibrium, that reaction quotient will be equal to K. So when the system is at equilibrium, this combination of concentrations of nitrogen, hydrogen, ammonia will equal a constant value. Let's do a couple more. This is a dissolution reaction of calcium chloride. Again, we can write the K as the products over the reactants. And so this would be the concentration of calcium 2+. Now the coefficient of that is 1, so we don't put any exponent in there, times the concentration of chloride. Again, a coefficient of 1, so we don't need an exponent. And normally we would divide by the concentration of reactants, but in this case our reactant is a solid. And the concentration of solids don't appreciably change. Their activity, their participation in the reaction doesn't appreciably change, and so they are omitted from equilibrium constant expressions. So in this case there is no product or reactant to divide by. We omit the solid, and this is our equilibrium constant expression. Pure liquids are the other example where we don't include them in the reactant equilibrium constant expression. So in this case, the K would be the concentration of the hydronium ion, H3O+, times the concentration of hydroxide. We wouldn't divide by the reactants because the only reactant is a pure liquid, and pure liquids aren't included in this expression. Now this particular equilibrium constant is a special one. It's the autoprotolysis of water and has the symbol Kw. Again, a capital K, but subscripts are often included for particular equilibrium constant expressions, in this case Kw. And in this case, this would be a solubility product constant. It's for a dissolution reaction of an ionic compound, and this would be a KSP.